Well, good morning, physics students. Here we are trying to do day two, um, trying to see what we can do. Today, we are going to start into this new chapter. I had you do a book assignment yesterday. I looked over what you turned in. Now, less than half of you turned in that assignment from yesterday as far as taking a picture. If there's a problem with you taking a picture of your assignment and submitting it, you got to let me know what's going on with that. Um, Certainly, yesterday was not 86 minutes worth of work by any stretch of the imagination. So you need to make sure that you are doing some time. Most of these days, probably not going to take our classroom time, much less homework time. So please, do the assignments that are coming up. Keep up with that. We want to keep some education happening here. With that said, I hope that things are going reasonably well for you at home. I know this is a brand new situation and we're all trying to deal with it one day at a time. So, um, today I want you to do some notes with me. And if you need to pause and get out your notebook, please do so as we go through the video. If you need to pause at any time, do so. Um, let's remember why do we take notes? It's because when you write things down, the actual physical act of writing helps make connections in your brain. Um, and I want you to be connecting with this material. You have to think about, what was it that Mr. Upplinger just said? What am I seeing on the screen? And you have to, then translate that into words that you're writing on paper. That helps build connections. And remember, our goal is learning. So I believe this helps, and I think there is research to support that. So please get out a notebook um, and follow along. We are going to go over some of the stuff that you would have had on your assignment yesterday. So if you did struggle with anything on the assignment yesterday, this should help clarify some things. All right. So, learning targets specifically for today, we're going to identify properties and characteristics of forces, and we're going to draw some free body diagrams. Now, if you did your assignment yesterday and you already have some of these things written down in your notes, you don't necessarily have to write them down a second time, but just look for things that you need to fill in. What are the details that can help you out? All right, so let's start out with what is a force? Okay, in very, very basic terms, a force is a push or a pull. Okay, we've used the example with vectors and said if you're teetering on the edge of the cliff and your best friend is behind you, they can apply a push or a pull. You hope in that case that they give you a pull and pull you back off the cliff. Um, but we know that that push or pull is going to affect us in some way. So, more so than what is a force, a push or pull, we want to know what do forces do. So, anytime forces are out of balance, something's going to change. There's going to be a change in the motion of the object. Unbalanced forces cause a change in the motion. I'm going to take a little more in depth look at that statement. An unbalanced force will change the motion of an object. Unbalanced force is also sometimes referred to as the net force. Now, if forces are in balance, then the net force is just zero. Okay, so there's always a net force. The net force is the sum of all forces on an object. And I'm just as I'm saying that out loud, I think that should get written in here. So net force is the sum of all forces acting on an object. And you can see that my typing skill requires me to look at the keyboard while I'm typing, and I'm a little slow. My apologies, but I would say that's probably one of my biggest regrets if I look back at school, is that I never learned to type. All right. So the net force is this. If it's an unbalanced force, it will change the motion of an object. And we just spent the last two chapters talking about how to describe motion. And if the motion is changing, we know that's an acceleration. Because if the motion is changing, the velocity is changing. Any change in velocity is an acceleration. It could be a positive acceleration, it could be a negative acceleration, or it could be something that we'll call a centripetal acceleration, which just causes a change in direction. Back to the balance forces result in no change in motion. So if there's no change in motion, there's no acceleration. That's an object traveling at a constant velocity. You can think of an example maybe. If you have a straight, smooth, level highway and you're driving a car with the cruise control on, all the forces are immense. There's certainly forces acting on your car. Gravity's pulling your car down. The road is pushing your car up. The engine is pushing your car forward. Frictional forces are holding back on your car. But because they're all in balance at that moment, you have constant velocity, no change in motion. I want to throw in here the whole concept of equilibrium. Equilibrium comes up in a lot of areas of science. And equilibrium is any situation where you have opposing changes happening at the same rate. So in our case, if we've got forces that are opposing each other, one force is this way, one force is this way, and they're at the same level, the same magnitude, then they cancel each other out and we have no change in motion. Now, in physics terms, we talk about two types of equilibrium. One is called translational equilibrium, where we have no net force, which means the object's not going to accelerate off in any direction. There's a second component to this that we'll be dealing with later in the year called rotational equilibrium, where there's no net torque. So I can have a situation where the object might not be taking off in space, but their forces might be out of balance that cause an object to spin or rotate. So there are torques that could be applied. It's still in translational equilibrium, but it's not in rotational equilibrium. In this, for the time being, we're going to be focusing on the translational part. The rotational part will come later. How do we measure a force? Well, in our American system, we typically use pounds. We might use ounces. We might use tons. But it's good for you to get into your head that pound is a unit of force. That means that weight is a measurement of force. Your weight is a force. Your weight is the force you are applying on the ground. Now, you may not have known that the English system has units of mass, and the actual English unit of mass is called a slug. I have no idea what the history is of that, but the English unit of mass is a slug, so a pound is technically a slug foot per second squared. And when you see all that together, well, then the metric unit of Newton seems to match, right? We got a unit of mass times a distance divided by a time squared. Distance over time squared is an acceleration. We've got a mass and an acceleration units that go together. English unit, pound. Newton is the metric unit. 1 Newton, capital N, is a kilogram times meter per second squared. We're not going to use pounds much. We'll be using newtons. And I want you to get this through your head. If we were in class, I'd be going around the room and I'd say, hey, Carson, what's a newton? And I'd expect him to say kilogram times a meter per second squared. And I'd say, Blake, what's a kilogram times a meter per second squared? And he'd say, a newton. And I'd say, Adam, what's a newton? And get the idea. I would go around the entire room repeating this over and over and over again. Get it in your heads. A newton is a kilogram times a meter per second squared. So, all right, little problem with labels. so let's say you had a mass of 75 kilograms. Then your weight, well, weight is a force. And how do we figure this out? If force is kilograms, it's got a unit of mass and it's got an acceleration. What acceleration do we use? We use the acceleration of gravity. Okay, weight is the force of gravity on you. We're going to use the acceleration of gravity. So we take 75 kilograms times 9.80 meters per second squared, and we get a mass or a weight of 735 newtons. And sometimes students look at, boy, a weight of 735 newtons. That's huge. No, we have probably several people in our classroom that are over 735 newtons, and we wouldn't consider them to be overly large people. Now, myself, I'm a rather large person, and I'm more like 1,400 newtons. Um, yeah, I've taken a little bit off, so I haven't done the math recently. So hopefully, I'm less than 1,400 newtons. But it's a lot of newtons. So when you see a person's weight in newtons, it is going to look like a larger number. Some of the smallest people in the room might have weights down around 500 newtons. For comparison, if you are stuck on your old American labels, 1 pound is about 4.45 newtons. All right, what else can we say about forces? Well, a lot of forces require objects to be touching, and these are called contact forces. All right, so if I have a ball and I throw the ball, I have to actually physically touch the ball. I have to push on the ball to make it go. If we're in a tug of war and I'm pulling on the rope, um, if your brother's smarting off at you and you just want to punch him, you got to make contact. Now, I say that nicely. Okay, no mean punching. Some forces can act at a distance. These are called field forces. So, an example: gravity. The sun keeps the Earth moving in its orbit, even though it's 93 million miles away, because of this massive amount of gravity between these objects. It acts at a great distance. Um, Magnetism is certainly something that you have seen. Objects, defying gravity, because the magnetic force at a close distance is actually stronger than gravity. So those are two examples that I think you are familiar with. Gravity, you don't have to be touching the Earth for gravity to affect you. If you try to jump off the Earth, gravity pulls you back. I haven't seen anybody, any of our athletes jump literally off the Earth and stay there. Gravity pulls them back down. Forces are vectors. That means they have a magnitude and they have a direction. Of course, vectors we represent on our paper diagrams with an arrow. The length of the arrow corresponds to the magnitude, and the arrow points in the direction. Remember that, magnitude and direction. So that takes us to the free body diagrams. So what's a free body diagram? Well, we show a representation of an object. You don't have to be real artistic. Those of you who turned in your assignments, I glanced at them. Some of you made very basic objects, which is fine, and some of you put lots of detail in them. I guess that's fine. Just make sure that you're not taking all the time on the detail and missing, some of the important factors. We also, in a free body diagram, then want to show all forces that are acting on the object. And we show a vector. The vector has to have a direction, and it should have some sort of length representing its magnitude. And I got to stress this, even in a sketch for a problem, you should try to get some representation of the size of these vectors. If one force is bigger than another, you need to make it a longer arrow. I saw on your last test one of the problems where one of the vectors was almost twice as big as the other, and almost all of you drew their size proportions in the opposite way. I don't know why that would be. Okay, the longer, the bigger the measurement, the longer the arrow needs to be. In order to get into the free body diagrams, your book didn't talk about normal force, and I really think we need to bring this in here right now. When an object is on a surface, let's just imagine you standing on the floor of your house, and weight's pulling you down, but you are not accelerating physically downward. You're not, moving faster downward. So what's happening? Well, it's because the floor is pushing back up on you. And that contact force between you and the room that you're in is called the normal force. The normal force is the perpendicular force of contact between surfaces. Perpendicular, always. Force of contact. So any object that's just on a horizontal surface, and if there's no other forces involved, then the normal force is just equal to the weight. So in a free body diagram, I would draw my object and I would have a downward arrow for my weight, and I would usually use F sub W for the weight. That's my force of weight. I have an equation here. It says equals m times g because weight is mass times gravitational acceleration. We'll add that in later a little bit. But my downward vector is my weight. Now, once I have my downward vector, I think, well, how hard does the floor push back? Well, if it's not sinking into the floor, if it's not accelerating into the floor, that force has to be equal and opposite. So the length of this vector is the same as the length of this vector. So what happens if we push the object down? So I want to start out with, we have a vector downward, and this is going to be the weight, right? So I'm going to call that FW. Doesn't look much like a W, it looks like a squiggle, but we'll get over it. Okay, now in addition to that, let's say somebody's leaning on this and pushing down on it. Well, then we have to have their force in here. So whatever that is, oops, forgot to go to my arrow tool, so we'll just make this an arrow. Now, what could I call that? How about if I call that F sub A P P for force applied? Okay. So we've got these two forces acting now. We've got the weight of the object plus whatever else somebody is pushing down on the object. Now, what's the normal force? Well, the floor is still not giving way. Let's assume that our structure is strong enough that this isn't sinking into the basement here now. So whatever these two together, the normal force has to match both of those. I should have used my arrow tool, but that's all right. We'll get that. So this is what I do for a free body diagram. I draw my object, I draw all my forces, and I label my forces. So I noticed that on some of your free body diagrams, some of you labeled some things, some of you did not. Here's the type of labeling that I would do. Fn for my normal force, Fw is always my weight. If I'm applying a force, I say F applied. Okay, what happens if we lift up on the object? Well, think about, first of all, the object has weight. Which way is the weight? The weight is down. So if the weight is down, I'm going to call that FW. Okay. Now, somebody's coming over and trying to pick up on it. Let's imagine this is our desk and somebody's lifting a little bit on the desk. And maybe they're not lifting it all the way off the floor, but they're lifting a little bit. But there's an upward force. So that's our applied force. All right. So now, what's our normal force? Well, our normal force is the perpendicular force of contact. So the weight acting downward is now being reduced by the upward force. Now, if this upward force is more than the weight, well, then they just lifted the desk and the desk is accelerating upward, so there's no contact force. If the upward force is a little bit less than the weight, and that's what I intended to draw, then the normal force is just going to be just enough to balance everything out. So it might be just a tiny little normal force upward that balances the rest of this. If the object isn't accelerating, so a desk on the floor, if it's not accelerating, all the forces on it have to be balanced. So we analyze and we look at, well, we got a weight, we got somebody's lifting a little bit on it, and whatever's left over must be the normal force. The really weird thing when you think about it is that the floor pushes back exactly as hard as it needs to. So when I'm standing on the floor is pushing back with a lot more force than, oh, let me think around the room. Caden Caston. You don't weigh nearly as much as I do. You're not applying as much force. But the floor somehow seems to know how much force to apply to you. The floor applies just enough force to keep everything in balance. Of course, occasionally there are disasters where the forces are out of balance. There's been situations where buildings fall down, buildings collapse. Um, we're not expecting that here. Okay? What if the forces are at an angle? Well, then we have to apply some of our past knowledge. So here we go. I've got an object. I've got its weight acting downward. And we have an applied force, but we're pulling upward at an angle. Well, if I got an angle, remember what we did with velocities at an angle? We broke them into components. We said how much of it was vertical and how much was horizontal. That's what we're going to do here. Okay? So now you got this vertical. Think about vertical is pulling upward, weight is pulling downward. If the vertical component is less than the weight, then the normal force has to make up for that. There's got to be a little bit of normal force upward yet to balance the weight. So in the vertical direction, all these forces are balanced. But if you look at this, there's nothing balancing the horizontal force. And if there's nothing balancing the horizontal force, this object is going to be moving this way. It's going to be accelerating, not just moving, but accelerating this way. Once it starts moving, another force that we might need to draw in here would be friction. So we are going to start seeing situations with friction involved. We're not just talking about throwing a ball through the air where the friction is pretty small. We're going to be sliding objects, across the board, across the floor. Friction is going to have to get involved. All right, so here's a diagram. I showed what if we're pushing down at an angle. So we know that the weight is down. We've got our applied force at a downward angle. We can take that applied force and break it into components, a vertical component and a horizontal component. Now in the vertical direction, we know the floor is going to support things. So we take our weight and our vertical component, and the normal force has to equal both of those. Again, the horizontal component is not balanced in this one, so there would be an acceleration to the side. And I'm going to throw a diagram in here. What if your object's at an angle? It's on an incline. So our object is on our incline. We got some slope called theta. Weight still acts straight down. Now, before I said if you had a force at an angle, you broke it up into horizontal and vertical. And whenever we have an inclined plane, we're going to also do components. But in this case, instead of finding horizontal and vertical, we're going to say how much of this weight is acting parallel to the incline. And so I use F sub P for my parallel. And how much of my weight is perpendicular to the incline. So I use F and I use a upside down T as a perpendicular symbol. Okay. Now we know our object isn't going into the incline, so the perpendicular force of contact is our normal force. So here's a good point. The normal force isn't just vertical. The normal force is perpendicular to the surface. So if our perpendicular component is pulling this way, the normal force is pushing back out. So the object is not going into or off of the incline, and our parallel component is going to try to make this accelerate down the slope. If any of you are skiers, maybe you can picture yourself right here. The steeper the hill, the bigger this parallel component gets, the more it accelerates you down the slope. So a couple basic examples. If I just set a ball on a table, well, its weight is acting down, the table's pushing up. That's the normal force. Simple. If I have a ball on an incline, the weight is acting down. The weight can be broken into a perpendicular component and a parallel component. The normal force is balancing the perpendicular component. The parallel component is unbalanced, so it's going to accelerate. So that's as far as I'm taking the video here today. I will be having you do a little assignment again from your textbook. That'll be in Google Classroom. Trying to move forward. I'm having you look a little bit. I think the next part is going to be on Newton's first law. We'll be talking about Newton's laws tomorrow with the class video, but I think this is enough for one video. I don't know how long it's gotten, but I'm sure you would like me to move on. Be sure to check your Google Classroom. Be sure to communicate with me if you're having any problems. I hope things are going well for you, and hope to see you all soon.